Section 4 starts out with a couple of examples for you to work on right off the bat, because these don't really involve anything I didn't already explain in Section 3. They're just kind of overflow. If I'd stuck them in Section 3 seemed a little too long to me. So these are a little different than anything I had you work on before. The first one kind of involves putting together Newton's second law together with some earlier, things back like at the beginning of the course. This is sort of an accident reconstruction kind of thing, which is one thing that can happen with people who are experts in this kind of thing. They get called into court every so often, and the guy who's been arrested is saying, there's just no way I could have stopped. The old lady leaped right out in front of me. And the prosecution is saying, no, he was going way over the speed limit and he was just driving recklessly and it was all his fault. So, well, skid marks are kind of a thing from the days before anti-lock brakes, actually. But if this guy was going down the road in his 71 Nova, anyhow, based on the information that's written here, the question is, how fast was the vehicle going when his foot first touched the brake pedal? It's kind of a two-step process. You can use F equals ma to get the car's acceleration, and then once you've got the acceleration, you kind of go from there. And maybe I've given you too many hints already, but pause it here, work on that. And here's how to do it, if you didn't already figure it out. If you did figure it out, and you're like, this is the easiest question ever, just scroll ahead a few minutes. You don't need to listen to me. So anytime you're doing an F equals ma problem, it's a good idea to start out with a diagram of the forces, although not as critical in this case because it's not a very complicated situation. You've got this is the car. If it makes you feel better, I'll put a couple little wheels on it. Looks kind of like a box car now on a railroad, doesn't it? Anyhow, it weighs something. There's a gravitational force pulling down, and the normal force pushing, that's the supporting force from the roadway. Actually, this would be the total of 4 different forces. You've got a force on each of the wheels, which, if you want to, get into the details, the forces on some wheels might be different than others, but this is just the total of all 4 of them. And then going horizontally, you have just the friction force. That's from the tire. If you've got the wheels locked up so the tires are dragging against the road, then there is no forward propulsive force from the engine, okay, like there would be if the wheels could turn. So, and this is a difficult point for some people. You've got the car moving in this direction, and people feel that for an object to move in that direction, there must be a force in that direction. And Aristotle would have agreed with you. But, like I kind of talked about last week, Aristotle on this particular occasion was wrong. Physics is really a very judgmental subject, you know. You take something else and it's like, well, we're reading this book, and what are the motivations of this character in the book? And one student in the class says, well, I think it's because of this, and somebody else in the class says, no, I think it's this entirely different thing, and both opinions are equally valid. And you're supposed, you know, if you write a good paper, you can explain yourself and get an A, no matter what your position. And in this class, it's kind of like, yeah, there's one position you can take, and if you don't, you're wrong. Anyhow, that's just the way it is. So the thing that's wrong here is that for an object to be moving toward the right, there must be a force pushing it. Earlier, some time ago, there had to be a force toward the right to get the car moving in the first place. But once it's going, it continues to move because of Newton's first law, okay? It moves simply because it's already moving. Rather, you need a force to make it stop, which is what this friction force is in the process of doing. So, as usual, you've got your choice. Is when you set up equations, is positive going to be that way, or is positive going to be the other way? And you're really free to do it either way you want, but I think the way most people would do it, that's supposed to be a plus sign. It ended up with a little tail on it somehow. I think most people would do it where the direction that the car is moving is positive. So summation of the forces in the x direction is equal to, well, in general, it's equal to the x, or forgot the m, that's kind of important, m times ax, the x component of the acceleration. So you look at your free body diagram. There is only one force in the x direction. In the y direction, these just cancel each other out and give you a total of 0. And in the x direction, but this is why the diagram is maybe not quite as important in this case as it was in some of the examples we looked at the end of last week's class. In the negative direction, you've got 8,000 newtons, and that is the only force that goes into this summation. It's the only horizontal arrow on the picture. Mass is 1,000 kilograms. You know it's the mass because it's in kilograms. I mean, the question doesn't come right out and say the car has this for its mass or has this for its weight, just says it's 1,000 kilogram car. But since a kilogram is a unit of mass, that can't be force or time or pressure or something else. It's so kilograms is m. Ax is equal to a because the x component is the only non-zero component the acceleration has. We're assuming here a level road, since the question doesn't say anything to the contrary. So, you know, the car is not moving upward or downward, and so the y component of the acceleration is 0, and therefore ax is just the acceleration. And so that's the rate this car is losing speed as it drags its wheels down the road. Now, part 2. From knowing that acceleration, and maybe I won't bother writing it out, but you know the distance that the car moved while it was dragging its wheels, and, well, it turns out, you know what, maybe I should write this out. Maybe I should be a good role model. So You know that. You know that the distance from one end of these drag marks to the other, the distance that the car moved while dragging its wheels, was 90 meters. And you don't actually know the velocity of the car at the end of the skid marks, but you can set a minimum. It'd be kind of hard to convince anybody that the car's speed was slower than 0 when it got, so we've got a minimum there. And from this minimum final velocity, we'll be able to establish a minimum initial velocity. Okay, what was the car's speed at the beginning of the skid marks? So you've got your nice little list here now, and you look at the formula sheet, hoping to find a formula that contains these 4 things, and sure enough, one is there. Fill stuff in. 0 squared is 0. Initial velocity is what I'm trying to find. And a couple lines of math. Which, if I remember right, is equivalent to something like 85 miles an hour, give or take. And so, yeah, this defendant has a serious problem. Because remember, that's just a minimum. Maybe he took his foot off the brake when the car was still moving. He could have been going even faster than this. Next one. The thing that's different about this one is that instead of having an object that you're trying to find some forces on, there's a system of objects. Well, I guess that actually is not too terribly different from this one here that we looked at last week. Here also you have a system of objects, 2 or more. In this case, they were objects at rest remaining at rest, so the sum of the forces was equal to 0. Here, they're in motion, they're accelerating, so the sum of the forces equals some other number. But either way, what you need to do, first of all, is decide which part of the system you're going to apply Newton's second law to. Okay, write an equation based on that, solve it, and now the question asks for more than one thing, so after you've solved the one equation, you write another equation where you apply Newton's law to something else, and then you solve that one. So why don't I turn you loose on this for a moment? And if you're just coming back and we're completely stumped, let me throw you one little hint before I show you all the gruesome details. There are other ways to do it that you can get to work, but what seems like the most straightforward thing to me is to find the tension in rope A, apply Newton's law to the whole 5-kilogram system, treat it as a single object. And you should be able to solve for force A out of that. And then to get the tension in the lower rope, apply F equals ma to just the 3-kilogram object on the bottom. So just in case that inspires anybody and they can get it now, I'll pause again. Okay, time for gruesome details. Number 2. So both boxes. So you got a rope, and here's a box, and another rope, and here's another box. And I'm just going to consider all of that as what's under consideration when I'm writing my equation. And altogether, that's 5 kilograms. 2 on top, 3 on the bottom, total is 5. There are 2 external forces. Pulling downward, the weight. Gravitational attraction to the Earth. Pulling upward, this is rope A up here. Tension in rope A. Now, you only have to worry about external forces, forces acting on this 2-body system from outside. The reason you don't have to worry about internal forces is because they always cancel each other because of Newton's third law. Well, I sort of didn't get to Newton's third law yet. That's coming up, I don't think it's next week. I think it's the week after that. But the third law says that when you've got things pulling on each other, the forces are always equal and opposite. So you've got a force downward. This box is pulling on that one via the cord that connects them. And likewise, the other box is pulling on, this one up here is pulling on the bottom one via the cord that connects them. And however many newtons well, you can peek at the answer. Turns out that's 23.4 newtons, okay? The force that the one end of the rope pulls down with is equal to the force that the other end of the rope pulls up with. So yeah, go ahead and put those forces in your equation if you want to, but you're going to have a positive 23.4, and you're also going to have sitting right next to it a negative 23.4, and that seems kind of pointless to me. So you really only need external forces. Summation of the forces in the y direction is equal to ma, because the y component of the acceleration is the only non-zero component there is. A is equal to ay because it's accelerating right along the y-axis. Every place there's a vertical arrow on the picture, it's one of the terms in the summation. So saying up is positive, I've got TA, tension in rope A, pulling up. And I've got 49 newtons pulling down. Mass is 5 kilograms. Again, don't confuse the weight with the mass. Once in a while I see somebody put 49 newtons in there, or a little more often I see somebody put 5 kilograms over there, and obviously either one of those things is going to change the answer. That whole judgmental thing again, it'll be wrong. And acceleration. It says it accelerates at 2 meters per second squared. So a lot of people would just put the 2 in there. Maybe if you're feeling really detailed, you'd write the unit next to it. And yeah, sorry to say, once again, wrong. A lot of people would get caught by that one. It accelerates downward. Got to pay attention to the directions of things that have directions. Mass is a scalar, so you never have to worry about a minus sign on that. Just like time is a scalar, it's never going to be negative. But acceleration's a vector. Don't ignore the direction. Without the minus sign, you get a whole different answer. Okay. Well, I think that's all the commentary that goes with this. I'll just mop up the math. Add 49 to both sides. $39 newtons. Maybe one more piece of commentary I should slip in here. Somebody might look at a situation like this and sort of naively say, well, if there's 49 newtons pulling down, there's got to be 49 newtons pulling back up, right? That's a pretty straightforward question. Only if the system is in equilibrium. Okay. We already looked at static equilibrium. That's when an object at rest is remaining at rest. There was two or three examples like that in section 3. What I haven't said much about yet is dynamic equilibrium, which is if you have something moving at a constant velocity. Okay, if this thing is going, I don't know, 4 meters per second, 4 meters per second, 4 meters per second, never speeds up or slows down, the acceleration is 0 in that case also, because acceleration means the rate of change and it's not changing. So there again, the summation of the forces would equal 0, and you'd have 49 up and 49 down to give you a total of 0. But this is not in any kind of equilibrium. It's not sitting still. It's not moving with a constant velocity. It says right there in the question, it's accelerating at 2 meters per second per second. Acceleration comes from an imbalance of the forces. So 39 up, 49 down. Therefore, it's falling faster and faster. If this force had been bigger, then you'd have an upward acceleration, and if they're equal, you have no acceleration. Acceleration comes from unbalanced forces. Anyhow, I've only done half the problem. Find the tension in both ropes. So now, let's just do a similar kind of thing, except it's going to be the lower box instead of the two-body system. So there it is. You've got rope B is what pulls up on the bottom box. Pulling downward, the weight of the lower box, which is 3 times 9.8, 29.2. Where did I get that? 29.4. That looks better. Okay. Just pretty much a rerun of what I did over here, just with different numbers. This one's up, That one's down. Mass times acceleration. Don't forget the minus sign. And that takes care of that one. Okay, so now you have seen lots of different kinds of problems solved with F equals ma. Let's go on from there. Let's look more closely at friction forces. I mean, they've come up already, like in this one back here, but all I've done so far is just, well, friction would have been 8,000 newtons. Well, how would you know friction was 8,000 newtons? Well, we're going to get into how you'd figure that out. So let's consider a sort of a little thought experiment. I mean, it's not that hypothetical. I'll do it right here for real in front of you. I've got a box and it's just sitting there. And then I start pushing on it just a little and it doesn't move. And I push a little harder and then it breaks free and then it does slide away. And so seen from the side, that would look kind of like this. Here's the box. And as usual, its weight pulls down. The surface it's resting on pushes back up. So W for weight. N is the supporting force. And let's use the letter P for push. There's me pushing on the box. And the surface, or the surface between the box and the piece of paper underneath it, resists with a force that I'll label with a lowercase f, F for friction. So if you go down to the fundamental level, friction depends on, there's a couple of things going on. One is roughness, okay? Even though this box looks pretty smooth to the eye, if you put it under like an electron microscope or something like that, you'd see what looks like mountains all over it. Same with a surface I was trying to drag it across. And when you try to slide it, the snags get caught on each other. So that's one factor that's at work, but it's not quite that simple. If it was, then it would sort of logically follow that if you had some really super smooth, highly polished, like a metal block sliding across a metal plate, and you polished it right down to some sort of optical grade smoothness, within a tenth of a wavelength of light tolerance. If friction was due to roughness, then it would follow that that makes it extremely slippery. And if you try that, what you find is exactly the opposite. Those things stick to each other like crazy. The other thing that's going on, aside from roughness, is basically bonding that occurs between the atoms on the top of one surface and the atoms on the bottom of the block, okay? If you've got a block made out of steel, okay, it's more of the atoms than anything else are iron, and what holds the block together as a rigid object is that each atom, each iron atom, or there's some other stuff mixed in, some carbon and so on, but these atoms, they share electrons, okay? If you've ever taken a chemistry course, this should be sort of a familiar sounding story. Metallic bonds come from sharing electrons, and in fact, the electrons get shared in such a way that they can't quite remember which atom they came from in the first place, which is what makes metals good conductors of electricity. Anyhow, same thing as what holds the metal plate together, that it's time to play Let's Pretend. Steel plate, steel block, okay? So if you put the atoms on the bottom of this block in close proximity with the atoms on the surface of this steel plate here, well, they're just dumb atoms, you know. That atom right there doesn't know it's supposed to be part of the block, and that this other atom right next to it is supposed to be part of something else. It just, you know, if you get them close enough together, they start sharing electrons. And when it's a nice smooth surface, a lot of the atoms on the bottom of this get nice and close to atoms on the top of this, and basically what amounts to microscopic spot welds start spontaneously forming across the surface, and that makes it sticky. Okay, so there are a couple of things going on that cause friction forces in the first place. But as far as how friction behaves, so let's say I start pushing on my little box. Well, maybe I'll even make a little table. Why not? How hard do I push? And the resulting force of friction. So first of all, before I touched it at all, when P is equal to 0, must be the friction force is 0, because this is an object at rest remaining at rest. And if friction was the, you know, I'm not even touching it yet. If this friction force was non-zero, it would be the only horizontal force acting on the block, which means the block would kind of crawl across the table on its own from that friction force pushing on it. And this is contrary to experience. Friction forces don't do that, okay? As long as this thing is an object at rest, remaining at rest, the summation of the forces must be 0. So if I push with 1 Newton, friction pushes back with 1 Newton. And if I push with 2 Newtons, friction pushes back with 2 Newtons. And so on until it breaks free. But as long as it's at rest, the forces just balance out. And so this is called static friction. Now, as I push harder and harder and harder and harder, obviously I can't go on like this forever. Even if this is something that I've super glued to the floor, I mean, eventually, if you back up a bulldozer and hook up the chains, you're going to be able to tear that off of there, no matter how securely it's bonded to the floor, okay? So there is some threshold beyond which static friction is not strong enough to maintain equilibrium. And when you reach that threshold, that maximum force of friction, I'll call it F max, that maximum force of static friction, where, like it says on the handout, the surface is just about to slip. It's still at rest right now, but if somebody just breathes on it, it's going to go. It basically depends on 2 things. First of all, it depends on how hard the surfaces are being pressed into each other. I can pull this clipboard across the table with a pretty small force. I mean, that's just a few ounces. Um, I'm not going to go to the trouble of measuring it. I think I've made my point. Probably like 3 or 5 ounces. It's a fraction of a pound, fraction of a Newton. If I had somebody come here and stand on top of that, it would probably break the desk, actually. But if I was doing this on the floor and I had somebody stand on it, then I would find I had to pull hundreds, probably thousands of times harder to make it slide. Now, it's still the same materials. It's still this stuff rubbing across that stuff, okay? But somebody stands on it, the surfaces get pressed into each other a lot harder, and that makes them grab each other a lot harder. The force with which the surfaces are being pressed together is this normal force that I'm talking about. It's called the normal force because it always acts normal to the surface, okay? In physics talk, normal means perpendicular. There are many different ways of saying that things make a 90-degree angle. Why have just one way of saying something when 3 or 4 different ways is 3 or 4 times as confusing, right? If things make a right angle, a lot of times they get called perpendicular. Mathematicians sometimes like the word orthogonal. Physicists kind of lean more towards the word normal. You know, every discipline has its own jargon. But the reason it's called that is, I mean, I drew this sitting on a level floor. But what if I had my little box and I tipped that a little too far. But if I had it sitting on a ramp, okay, so I've got that up around 12 or 15 degrees at least. Seen from the side, there's my box of staples sitting on my clipboard. And pull of gravity always points directly toward the center of the Earth. But the normal force is always normal, meaning perpendicular, to the surface it's sitting on. And of course, as long as I've started the diagram, I might as well do a good job with it. There would also be the friction force. One way of looking at this is to say, because this block is in contact with this surface, there is a force because of them being in contact, okay? It is often convenient to break that contact force into 2 components. So the total complete force from this block being in contact with this clipboard is probably in that direction, somewhere around there. Maybe not exactly opposite the weight, but it would depend on whether the block is accelerating or not. But roughly, at least, in that direction. Well, it's often convenient to say that this contact force is a resultant of 2 parts. The component that's parallel to the surface we call the force of friction. And the component that's normal to the surface we call the normal force. Okay? So the normal force, that's how hard this is being pressed against that. And that's one of the factors that determines how far you can go before the thing breaks free and slides. In the lab that goes with this part, I don't think that's lab 4. I think it's actually lab 5, unless it isn't. Well, whether it's 4 or 5, you will, in the not too distant future, do an experiment that's pretty much exactly what I was just doing with this box of staples, only it's going to be a wooden block sitting on a wooden board. and you tip it steeper and steeper, and you're looking for the angle where it lets go and slides away, which this is going pretty far. There it goes. Okay. So when you're right on the edge, just before it breaks free, maximum friction is equal to mu times n. Well, what if, oh, this, by the way, for those of you unfamiliar, what? You're unfamiliar with the Greek alphabet? I've often thought we ought to start this course out kind of like they do in first grade. It's like you could learn the little song. Alpha, beta, gamma, delta, da, 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 da. Anyhow, this is the Greek letter mu, okay? It's the Greek version of the letter M, and that's pretty much a standard symbol for the, it gets used for other things too, just like regular letters get used for more than one thing, but it is the symbol that's generally used for the coefficient of friction. Now, once the thing breaks free, okay, once I'm pushing hard enough to make this slide across the floor, or once I've tipped this far enough that it'll slide downhill, now you're dealing with what's called kinetic friction. Maybe I should put this thing back. So, static friction, kinetic means sliding friction. I think the main reason we don't just call it sliding friction is then you'd have S for static and S for sliding, which would make the whole subscript kind of pointless if you did that. So we'll call it kinetic friction, so we got a different letter. But that's what it means. The force of kinetic friction is a similar story. There's a coefficient of kinetic friction, which generally is less. Yeah, kinetic friction is usually weaker than static friction. Sometimes they might be pretty close to each other, but kinetic would never be stronger. If you've got the surfaces sliding across each other, they just simply can't get as good a grip on each other as when you let things settle in, okay? So kinetic friction would be weaker than static friction. To me, the classic example of this sort of thing is, so those of you who are not mechanically inclined have probably never had the privilege of having this experience, but let me just describe it to you. You're trying to get a spark plug out of an engine, okay? You know, it's been in there like, I don't know how, 50,000 miles or something, and it's like, it's time to get some new ones in there. So you're pushing on the wrench, and it won't go. So you push harder on the wrench, and it still won't go. So you really lean right into it, and it lets go, and your hand whips right around in a circle, and you punch the alternator, and it knocks all the skin off your knuckles. After you've done this sort of thing a few times, you think somebody would be smart enough to wear a glove when doing that sort of thing, but yeah, we're not always that smart. Well, I'm oversimplifying a little bit here. I mean, there are changes in the normal force going on also once that thing loosens up. But to simplify the story a little bit, when you're pushing harder and harder, trying to get that to move, you're dealing with static friction. Well, you finally get to the point where you've reached mu s times n, and you push harder than that, and it lets go. Well, now, all of a sudden, before you have time to adjust how hard you're pushing, now you're dealing with kinetic friction because the surfaces are sliding across each other. The threads on the spark plug and the threads in the hole, those surfaces sliding across each other are now in motion, and friction got weaker, and now you're pushing too hard, so your hand rapidly accelerates, and it doesn't end well. So that's kind of the idea of this. There is a table of friction coefficients toward the back. I really ought to find the formula sheet for your course instead of always waving around the one for Physics 131. But that's still the one that I've got sitting right next to me here. And the formula sheets are extremely similar. So it may not be on page 7 in yours. Maybe it's page 6 or something like that. But aside from all the formulas in the formula sheet, there are several tables for you to refer to toward the back. And one of them, you can look up friction coefficients. And it's not a very extensive table. I mean, you can find tables like this in handbooks that go on for pages, but just as a few sample materials. So like steel on steel. Coefficient of static friction is around 3/4. Coefficient of kinetic friction is a little over 1/2. And so you can refer to that during a test if you need to. If all the question tells you is that it's steel on steel, you go in there and you look up the coefficient of friction. So that's all about how you would find the magnitude of the friction force, whether it's at rest or whether it's sliding. I should probably put a little footnote on all of this in that friction can actually be kind of a temperamental, complicated thing. And this is a somewhat simplified picture, okay? We have, for example, assumed that the speed, with kinetic friction, we've assumed that the speed that the block is sliding across the floor or that the wheel is dragging across the pavement, we've assumed that, you know, the velocity doesn't appear in the formula anywhere. So it's independent of the speed. Yeah, that's a pretty good assumption for most materials most of the time, unless you're going like really, really, really fast. But don't expect it to be perfectly true regardless. We've assumed the area of contact doesn't matter. There again, that's, you know, if the box is sliding across the clipboard that way, or if I turn it so that it's a smaller area of contact, we're assuming that doesn't matter. You know, there again, that's a pretty good approximation for most materials, as long as you don't go to extremes where you've got this little tiny area of contact that's going to dig into the surface, you know. If you're trying to slide a wire brush across a surface where it's just all those little points, that's going to be a little different than having a large smooth object. But anyhow, these are not some basic fundamental laws of nature. This is a model of friction that works pretty well for most materials most of the time. So that's how you get the magnitude of the force. For the direction, just remember the catchy little phrase, friction always opposes motion. If I'm pushing it that way, friction's going to point the other way. Okay, the rest, here again, just like with section 3, I think I'm just going to go all the way through in one single recording without bothering with a break. And the beauty of taking this course by video is you can stop and make yourself some popcorn anytime you want. So the idea is you're going to do these two based on what I've just said. And then I'm going to do this one for you to use as a pattern in doing that one. Although if you're up to the challenge of seeing if you can do this yourself before I show it to you, I mean, so much the better. You know, the more you can do this sort of thing, the better. But pause here. And now I'll go over number 3. So you are in an amusement park ride, and yeah, when Years ago when we were at Disney World, my daughter talked me into going on the Tower of Terror. I don't generally like rides like that. I know most of you just think they're riotous fun, but um, anyhow, you get to a certain point in the ride, and it basically drops you. You're sitting in this room. And the room goes down. So in the Tower of Terror, I think you go into a free fall, actually, at least that fast. Well, this one may not be dropping you quite that fast, but whatever the rate of acceleration is, there is you sitting in your seat. I have said many times, there is a reason I was a physics major, not an art major. But, you know, for purposes of the physics, representing a person as a block is, for most purposes, just fine. So you weigh something, W for weight. And the normal force, due to contact with the surface that supports you, that's pushing back up. Compare the normal force to your weight. Well, if you are, it's like I was saying when I was going over that other one a little while ago, when I was talking about this, it's like, you know, well, why is that just 39 if this is 49? Acceleration comes from an imbalance in the forces. For it to accelerate downward, the force down has to be more than the force up. You might remember me saying that. It's the same exact sort of thing here. If this person is accelerating downward, then the net force has to be downward, which means this one is bigger than that one. So from sum of the forces equals ma. Said it backwards. A downward acceleration, which is what the question told us is going on, downward acceleration means a downward net force, and to have a net force in the downward direction, the weight has to be bigger, the normal force has to be smaller. Among the reasons I wanted to look at this question is to try and nip in the bud the idea that the normal force is the same thing as an object's weight. It's like, oh, well, if it weighs 15 pounds, then the normal force would be 15 pounds. If it's an object at rest, remaining at rest, and there are no other vertical forces, there's a lot of ifs there, then yeah, this would equal that in that case. But it's just as easy to come up with examples where they do not equal each other. So, you know, maybe this is a 150-pound person and the normal force is only 50 pounds because they're accelerating downward at a pretty good pace. So the normal force and the weight are two distinct things. I mean, the weight is a gravitational force. The normal force, ultimately, if you go to the fundamental level, is electromagnetic in nature. All of those atoms on the bottom of you do not want to pass through all those atoms on the top of the surface. The electron clouds in the outer parts of these atoms are repelled by the electron clouds in the outer parts of the, they're negative charges, like charges repel. And, atoms are almost entirely empty space. There's plenty of room for you to just melt right through the floor and go right down to the center of the earth. But the reason you don't is because of electrostatic repulsion. The electron clouds on the surface of these atoms repel the electron clouds on the surface of those atoms. So that's what any kind of contact force is, whether it's the normal force or me pushing, the force from contact with my finger. They're all electromagnetic in nature ultimately. So anyhow, two different types of forces that do not necessarily have to equal each other, and we will see some more examples before today is over where they aren't. I suppose maybe I should put my customary box around the answer to the question. Here's where we pause and you work on number 4. And now here's where you come back and I explain number 4. Yeah, I didn't put the answer at the bottom of this one. I do that sometimes when I figure that if I just put the answer there, it would give the whole thing away, and there isn't even any point in asking the question then. But for those of you who have been waiting impatiently to know the answers, part A is 10 newtons, part B is any force greater than 20 newtons, and part C is 12 newtons. And the details go like this. Part A. So the block is at rest, and that force P is either, doesn't matter, it could be either way. Either somebody's over here pushing on the one side of the block, or there's a string tied to it, and they're pulling on the string on the other side. Push and pull both happen to start with the same letter, so I don't have to decide. It could be either one. But whichever it is, you got 10 newtons that way. And part of the question says it's at rest. To be a little more specific, maybe I should have said it's remaining at rest. An object's velocity can pass through zero without it being in equilibrium, but if it remains at rest for any finite time, the forces have to balance. So if you've got if you've got 10 newtons pulling the one way, you got to have 10 newtons pulling the other way in order to, plus 10 minus 10, that'll give you the total of 0 that you have to have for the thing to be in equilibrium. Now, the popular way of doing this wrong is, for any of you who'd prefer to do it that way, is to look at it and say, well, let's see, it says the block is at rest, therefore I'm dealing with static friction, so I'll look up the coefficient of static friction, and it's 0.5. You get it out of that table in the formula sheet, and you multiply it by the normal force, which is 40 newtons. That's true, that part of this is correct. So 0.5 times 40 equals 20. 20 is the answer to part B, okay? Mu times n does not tell you what the static friction has to be no matter what. It simply tells you the upper limit, F max. Okay, if you look back at the previous page, it isn't equals, it's less than or equals, okay? F is equal to mu s times n only if motion is impending, only if it's right on the edge of slipping away. Well, there's nothing in part A that says that's the case. Actually, you're not pulling nearly hard enough to make it start to move. So mu times n is irrelevant to part A. What matters is that it's at rest. Part B, how hard do you have to pull to start it moving? Okay, so now we're interested in what's the threshold. What's the hardest that friction can pull back? So you look it up in the tape. Now, wood on wood, it says 0.5. From that table. So from the table, for wood on wood, this is just a typical value. Like when you do the lab that I was talking about, where you tip the thing, and you're supposed to determine the coefficient of friction, that's going to be wood on wood. Do not necessarily expect to get 0.5. I mean, wood on wood is a good deal more vague than like steel on steel. There's all different kinds of wood, you know. Is it softwood or is it hardwood? Is it well sanded or kind of rough? So this is what we're going to use as a typical value, but as they say in the commercials sometimes, your results may vary. That's the end of the commercial where the guy talks real fast. Normal force. Well, I just got done with a rant about how the normal force does not necessarily equal the weight. But this time it does. I'm using a lowercase n for the normal force, so it doesn't look like the capital N that I'm using for newtons. In this case, you've got equilibrium. Some of the forces in the y direction equals 0. And there are no forces in the y direction besides this and this, so they have to equal each other and balance out. So, but it's worth pausing to think about that and make sure you don't assume something that's not true. Well, the maximum that friction can withstand is 20 newtons. So if you pull with 20, technically it would still remain at rest. But if you go to 20.0001, then it's going to let go. So why don't we just write it this way? Any force P, which is greater than or equal to 20 newtons. Well, actually, it wouldn't be, well, I should have said greater than, not greater than or equal, but as a practical matter, a more realistic way to say it would be just something around 20 newtons is where it's going to let go. Because as I said, this is going to vary from one, even if they're both pine, you know, this is going to vary a little bit between one board and the next. It's going to vary between different spots on the same board. So somewhere around 20 newtons is where, if you pull that hard, it'll let go. So then part C, now it's let go and it's sliding along. How hard do you have to pull to keep it going at a constant speed? You could always pull harder than that, which would make it accelerate, but the minimum needed to keep it moving indefinitely would be if you just maintained its speed. So at a constant speed, some of the forces in the x direction is 0. I've had people ask me, well, how do I know when to set the sum of the forces equal to 0, and how do I know when to set it equal to m times a? And the answer is the sum of the forces is always equal to ma. That is a basic law of nature, okay? That is something that's true everywhere all the time. But if something is remaining at rest, a is equal to 0, which makes m times a equal to 0. Or if it's moving at a constant speed, so-called dynamic equilibrium, again, acceleration is 0. So if the forces are going to balance, P is equal to the friction force, just like it was in the static case. Sliding friction is always equal to mu k times n. So you look in the other column of the same table that you got the 0.5 from. The other column is where they've got the coefficient of kinetic friction, and what's given there is 0.3. The fact that these are not very precise, by the way, is the reason that they're given to only one significant figure. Because you can't go to the next decimal place without starting to get real specific about exactly where are you on exactly which board. So even though it took 20 newtons to make it start moving, you can keep it moving if you pull with something in the neighborhood of 12 newtons. Okay, so I was going to run through 4A, so you could use that as a pattern to do 4-5, I guess is what I called it. Now, just in case you don't have your own copy of the handout right there next to you, we'll lay it there for a moment so you can see what I'm working on. It says a 5-kilogram block. It's a situation a lot like this problem you're going to work on, except on the one I was going to do, I didn't bother to include a picture. I just described it in words. But in this one, it's 5 kilograms instead of 10. It's pulled by a rope, kind of like this rope, only my rope is going to be 40 degrees above the horizontal where yours is only 20. I'm pulling the rope with 35 newtons. It gives the coefficient of kinetic friction. And the question is, what is the rate that this thing is picking up speed? What is its acceleration? So it's an F equals ma problem. We're going to solve for A out of Newton's second law, is basically how we're going to answer that. And as I believe I mentioned last week, the first step in any kind of F equals ma problem, whether it's a statics problem where the forces add up to 0, or here where it's a dynamics problem, first step is the free body diagram. So I have a 5-kilogram block. And I'm pulling it with this 35 Newton force, which acts 40 degrees above the horizontal. I'll bet that's just a little on the low side. I'll bet that's like 35 or 38 degrees or something like that. Anyhow, diagram is not to scale. Other forces, the weight. For the 1000th time, the weight is not 5 kilograms. The weight is equal to 5 kilograms times 9.8. Maybe think of it this way. You're going to throw these forces together into some sort of a summation. A summation means to add. In order to add numbers, they have to be in the same units, okay? If I ask you, how much is 5 gallons plus 3 weeks? That is a really bad question. That makes no sense whatsoever, even if they're both units of length. If I ask you, how much is 3 feet plus 7 inches, that is not 10 feet or 10 inches. Okay, numbers have to be in the same units if you're going to add them. So if all the other forces in your summation are in newtons, don't you think the weight should be in newtons also? Something to keep in mind. As the block gets dragged across the floor, there is friction. And there is the normal force. The floor creating a supporting force perpendicular to the floor. Okay, so step one, identify all the forces by sketching them on a diagram. This is sort of another step here. I've actually figured out how big one of them is already. But sooner or later, probably more like sooner, step two, you get to step two, which is components. That one, and that one lie right along either the x or the y-axis. So finding their components is trivial, and I don't have to write anything down about it. This one acts at an angle, so I got to do the thing about sines and cosines. Hypotenuse times sine is the opposite side of the triangle. And as we've seen a number of times before, hypotenuse times cosine is the adjacent side. Okay. So this block is accelerating in the x direction. It's a horizontal floor, and the block is, you're not pulling on this rope hard enough to lift it off the floor. So it's going to just slide right along the floor. It's accelerating in the x direction. So it's the x equation. Remember, like I said when we were doing projectiles, when you're dealing with vectors, think in terms of components. It's going to be an x equation and a y equation, just like there were x and y equations when you were calculating where a projectile would come down, only this time it's equations full of forces instead of, velocities and things. Anyhow, the thing we're looking for is going to come out of the x equation. The problem is, right now, the x equation will contain another unknown. We not only don't know the acceleration, we don't know the friction force. One equation with two unknowns in it, you can't solve it. Well, we could get the friction force from F equals mu k times n. The thing is sliding, so we're dealing with kinetic friction. We've got the coefficient of friction. It was given in the question. If we're going to use F equals mu times n, we need to know the normal force. So the place to start is to figure out the normal force. So that's the strategy. And then to start actually executing that strategy, summation of the forces in the y direction equals 0. Because it is not accelerating up or down. AY is equal to 0. It's accelerating along the x-axis, so AX equals A, AY equals 0. Vertically, the forces have to balance. Every place there's a vertical arrow on this picture, it becomes one of the terms in this summation. There are 3, there, and there. So here I've got an arrow with an N next to it, and it points up, so that one's positive. Here I've got a vertical arrow with a 22.5, and that points up, so it's positive. And there I've got an arrow that's 49, and it points down, so it gets a minus sign. So add 49 to both sides, subtract 22.5 from both sides, and when you put them together, the normal force is 26.5 newtons. So notice again what I was saying earlier. The normal force does not necessarily equal the object's weight. I've had people come to my office for help on homework, and they say, well, let's see now. The friction force equals the coefficient of friction times the weight. No. What's going on in this case is that the block is partially supported by the upward component from the rope. The normal force only has to make up the difference. The normal force doesn't support the full weight because it gets help from the rope. Once I know the normal force, then friction is mu k times n, and that's, let's see, 0.57 is given in the question, times 26.5. And somewhere here I've gotten, that's where I wrote that, 15.1 newtons for the friction force. And maybe it's worth writing down for extra emphasis. Should have done this a minute ago. Notice the normal force does not have to equal the weight. Now that I know there's 15.1 newtons of friction, now I can get my answer out of summation of the forces in the x equals ma. And every place there's a horizontal arrow, that's a term in this summation, and there's two of them, 26.8 to the right and the 15.1 to the left. So 26.8 minus 15.1 equals, the mass is 5 kilograms. .34. How consecutive? Okay. So number 5 is pretty much the same problem all over again. Just gotta, well, try and figure it out for yourself as opposed to just using this for a template that you just mindlessly throw numbers into. Try and repeat the thinking process that I went through. You don't want to memorize your way through problems, because when a test comes around, all I have to do is tweak some little detail, and people who've just memorized everything will kind of fall apart. So you need to be going through the thought process. Why am I doing this? Why am I doing that? Rather than just, well, I'm doing this next because that's what he did. So pause here. And if you got 1.46 meters per second squared, there's a pretty good chance you don't need to listen to me go through this because it's going to sound an awful lot like me going through the one I just finished. But, and this is the last thing on this recording. Well, no, actually it's not. Wait, stop. Don't stop playing it yet. Coming up next, hopefully nobody's already signed out. Well, I'm just going to repeat some of what's written here anyhow. The last couple of pages in the handout here are a review for the exam that's coming up soon. This review has the same format that the actual test will. Okay, the format that I use for my tests is that they have 5 parts, each of which is worth 25 points, and the best 4 out of 5 count. Okay, you may have taken other tests where they say, well, if you do all 5 parts, I'm just going to look at the first 4. Well, that's what somebody else likes to do. In my case, it's going to be the best 4 out of 5, not the first 4 out of 5. So the best strategy here is to do the whole test, because I don't really time you anyhow. So it's not like you're going to be running out of time. Do the whole test and let me cross out the worst grade. Okay. The first 4 parts are each going to be problems. They are not going to be the 4 problems that I have here, but they will be other problems on sections 1 through 4. And then the last part will be a collection of little 5-point questions. Again, not the same ones that are here, but similar kinds of things on the same subject matter. Where this came from is years ago, before a test, there'd always be just 1 or 2 people who'd show up at my office and say, hey, can we have a copy of last year's test to study from? And I'd say, oh, sure, I got a couple copies of it left, and I'd dig around in my file cabinet. Here you go. And after a while, I said to myself, why don't I just give everybody a fake test, and then they won't have to ask me for it? So that's kind of where this comes from. When you want to see how I did it, I've got complete solutions written out on the website. The website where you go to look at the homework solutions, there's several different things you can click on there, and one of them says review solutions, and you go in there and you'll see this sort of thing. Line by line, how did I do it? Okay. The actual test may actually be slightly easier than this one, because where I get questions for sometimes for the review is I'll give an exam and there'll be one problem that's like just just a bloodbath. They just had no idea how to do that, did they? And maybe I'd better put that on the review so they take a closer look at that kind of thing while they're still studying. So there is sort of a bias toward harder than average questions sometimes on these reviews. But don't just study only this. You need to go back through everything we covered. Just because there's a projectile problem on this test doesn't necessarily mean there will be a projectile problem. I mean, I have probably 10 or 12 old tests. I've taught this course a lot of times at this point, and I've probably got maybe not quite a dozen, but close to it, and tests in my drawer. And sometimes I get them out and use them over again. Once in a while I get ambitious and write a new one. But, first exam, some of those old tests have a projectile problem. Some of them I asked something else out of section 2. Maybe I had him do the head to tail vector addition. Okay, so don't try to outsmart me. Review everything I've covered. But this gives you some idea anyhow what a test looks like, and also gets you to review some things that I thought might be particularly troublesome. So anyhow, I wanted to run through that little explanation of what's going on with the review sheet here. So now, if you didn't have any trouble with number 5 and don't want to watch me go through it, you can leave the video. Hopefully you didn't already about 10 minutes ago. But for those of you who would like to see me go through this one, this will be the last thing on the video. If I can, there it is. Okay, diagram. Same picture, just with different numbers. 10 kilograms, which will weigh 98 newtons. And this time, just a second. Okay. This time the rope makes a 20-degree angle with the horizontal, and it's being pulled with 50 newtons. Got X and Y components like that. And there would be the normal force, and there would be the friction force. Opposite side comes out 17.1 newtons. Adjacent side is 47. Got to figure out the normal force. Sum of the forces in the y direction equals 0, so n plus 17.1 minus 98 equals 0. You should have gotten 80.9 for the normal force. Once you know that, F equals mu k times n. Coefficient of friction is given in the question. Coefficient of friction, by the way, is a dimensionless number. I probably should have mentioned that earlier when everybody was still listening. But if you look at, think of the units on mu equals F over n. Just take this, divide both sides by n. Newtons over newtons or pounds over pounds, whatever you measure the forces in, units cancel each other out, and you're left with just a pure number that would be the same in any system of measurement. Okay, if the coefficient of friction is 0.25, that means this force is 4 times bigger than that force. And that would be true whether you measure it in newtons or pounds or ounces or anything else. So a dimensionless number times newtons gives you newtons. So we got a little over 32 newtons of friction. Once I know that, I can get the acceleration out of sum of the forces in the x equals ma. I've got 47 to the right. I've got the friction force, which I now know is this, pulling to the left. And there you go. Okay. So that's everything that's on the first exam. The stuff on the second exam is the second packet of notes, which you can find in the website and print it if you'd like a hard copy.